Welcome to Lecture 26 on Applied Optimization. In this lecture, we look at real-world problems and we apply the derivative to solve solutions to problems we're interested in. So we might consider problems such as these that I have written on the board. So what is the shortest possible path to my destination? You might want to know what combination of routes you need to take to basically minimize the travel time. Or maybe what dimensions do you need to build a certain structure so that you're using the least amount of surface area so to minimize your cost. So we're going to look at problems where we have many variables going on, and we're going to look for ways to minimize or maximize something we're looking or hoping to get. So this whole process that I'm talking about is called optimization. So I'm going to give you a kind of loose definition of what that is. So optimization, it refers to finding the best, I put that in quotation marks, the best solution given a set of variables subject to some constraints. And you can think of these as like limitations or just some extra thing going on in the real world that limits what we can actually do. So these are some kind of limitations or constraints. And usually, this involves finding absolute extrema. And this is something that we've seen very recently in our previous lectures. So a lot of these problems boil down to finding the absolute max or absolute min of a certain situation that you've written in some kind of symbolic form. So here's our method that we're going to go through to solve these types of problems. So this is the method. Just like related rates, the first thing I want you to do is always to draw a picture, especially if the situation is very complicated to visualize. I want you to draw a picture first. The second thing you'll do is you'll assign some variables. So you're going to assign variables based on the different unknowns that you see in the problem. Next, for 3, you're going to find an equation, or it could be multiple equations. So find some equations relating the variables that you just defined in step 2. After this, you're going to want to eliminate all but one variable. This is important because I want to find absolute maxes and mins, and in Calculus 1, I'm doing that with one variable. So you want to eliminate all your other variables, and then after you've done that, you can go ahead and differentiate your function. So whatever you've created, you're going to differentiate that function. So this is the method we're going to stick to. Today I'm going to do 3 examples that kind of illustrate this process. Okay, so Movie Magic, I have presented the problem on the board for us. It says, a farmer possesses 1,000 feet of fencing and would like to build a rectangular enclosure which maximizes the area for his livestock to roam. It's important to have lots of room for your chickens and cows to run around, of course. I would not be a good farmer. I would just want my animals to be happy, and that's it. Maybe that does make me a good farmer. So find these dimensions that maximizes the area, and you only have this much fencing. All right, so let's draw the picture. This time, so for 1, the picture's not so complicated. I have to draw a rectangle, so I'm going to draw a rectangle. So there it is. I know that I have 1,000 feet of fencing, so that is called the perimeter. So I know that my perimeter is 1,000 feet. I should assign some variables to what's going on. So the 2 things I need to worry about here are the length and the width of the rectangle. So for 2, I'm going to say, okay, well, this is going to be the width, my x, and y is going to be called the length. For 3, I need to find some kind of equations relating the variables together. So I have the perimeter is 1,000. So you could say perimeter is the distance all the way around. So that's 2 of these x's plus 2 of the y's. And I know that's 1,000. you can do even better with this and divide everything by 2. So x plus y is 500. And you can think of this as my constraint. My x and y are limited by this equation. So that's what I meant over here by some kind of constraint happening on the situation. So we have a constraint here. What other equations do I know? Well, I'm trying to maximize the area. This is the whole point. I'm trying to optimize this situation. So my area formula is length times width, right? Well, what I would like to do in 4 is I want to eliminate all the variables but 1. So I'm going to say a of x equals, instead of y, I'm going to go over here and I'm going to solve using my constraint that y is 500 minus x. And then this can be plugged into this equation here. So area is x times y is 500 minus x. This means that the area is 500x minus x squared. So in this step, I've eliminated all my variables but 1. And then 5, I'm going to go ahead and I'm going to differentiate this. And I'm going to try to find the maximum area. So to find absolute maxes and mins, you find the derivative and find those critical numbers. So derivative of this is going to be 500 minus 2x. And I need to set this equal to 0 because I'm looking for the critical numbers. So are there any critical numbers? And that's where the derivative, we're not dealing with the function f, sorry about that, it's a. We're looking where the derivative equals 0. That gives us some of the critical numbers. Set this equal to 0. 2x is supposed to be 500. And so x equals 250 is one of those critical numbers. It's the only one I see here, actually. OK, so it would be nice to know if this was an absolute max or min, right? So let's look at the second derivative and use the second derivative test just to verify that. So this is going to be the second derivative test right here. What is the second derivative of a of x? Well, I do another derivative of this. It's going to be negative 2. So a prime of 250 is 0. And I have a double prime at 250 is what type of number? Well, the second derivative is always negative 2. So that means this is negative. So by the second derivative test, we know that x equals 250 is a maximum. OK, so just checking that this was actually indeed a maximum. So this x value right here is going to maximize the area situation. So the dimensions here should be 250, 250. Well, if y has to be the same thing here, and I've already used 500 feet of fencing, these also have to be 250. So my final answer is that the pen I need to build here would be a 250 feet by 250 feet rectangular pen. OK, so that was just our first example in using this process to find an absolute maximum. I'll return in just a moment. We'll do 2 more examples. So see you soon. Welcome back. So these are the final 2 problems we're going to look at today. The first one says, a box with a square base and no top will have a volume of 100 centimeters cubed. Find the dimensions of the box that requires the least amount of material for its 5 sides. So the last problem, you're trying to maximize area. You wanted a lot of area for your animals. This one, you want to minimize the amount of material on the box because maybe it increases the cost or something if you have a lot of material. So this is the situation we have here. For one, I'm going to draw a picture, as I did before. So please don't make fun of my artistic skills here. So I have some kind of box here. And you have that there are 5 sides, including the bottom, but there's no lid for the box. So in total, there's going to be 5 sides for it. The base is said to be square. So for the dimensions of the base here, the length and the width, I'm going to put x. We don't know anything about the height, So I'm just going to call that y. So what I'm doing right now is I'm assigning x to be the base length, and then y is going to be the height, which could be different from x. So that's me assigning my variables. Now what I'm going to do is I'm going to find some equations. So one equation that I see I'm going to need is the volume formula. So I would reread the problem, maybe see that I'm talking about volume. The volume of a box like this is length times width times height. So this is x times y, which is x squared y. And this is equal to 100. That's given to us. So you can think of this as our constraint. So this is something that's happening, a relationship that's happening between the x and the y variables that's limiting the possible answers here. So this is our constraint. What am I trying to maximize? Or sorry, minimize. I'm not trying to maximize anything. I'm trying to minimize the amount of material for the sides. That's known as surface area. So for our surface area, what you need to do is you need to add up the area of every single side, and there's 5 of them. So what's the surface area of the base? Well, it's the area of the base. So that's x times x. So that's x squared plus, what's the area of these 4 sides that wrap around the box? Well, all of these heights are y, and these lengths are x's. So I have 4 of them. If you think about all the sides, so you have 4x times y. And that's the total area of all 5 sides. What I'd like to do is I'd like to minimize this. So that means I will be taking a derivative. However, step 4, I have to eliminate all my variables but one. So I'm going to eliminate this y variable. I think that's the easiest thing to do. So we know that x squared y is 100. So that means y should equal 100 over x squared. I'm going to assume the length of my box here is not 0, so I can divide by this. And it shouldn't be, right? It's an actual box. So then take this equation here and plug it in right above here for the y of the surface area formula. So I'll call surface area capital S. It'll be x squared plus 4x, and instead of the y, we're going to replace with this new equation I made, 100 over x squared. So this is equal to x squared plus, and then I have 4 times 100 is 400 over x. And then from here I could rewrite this as x squared plus 400x to the negative 1 power. Okay? And then finally, what I'm going to do is I'm going to differentiate this. I want the critical numbers for this so that I can find out where I have a minimum. So I'm going to take the derivative. S prime of x is 2x. Bring the negative 1 in front. I get negative 400 over x squared now. That's the derivative. And I'd like to know where this equals 0. Okay? If I add this fraction to the other side, I get 2x over 1 equals 400 over x squared. If you cross multiply, you get 2x cubed equals 400. This tells me that x cubed is 200. And then this would tell me, if I cube root both sides, x should be the cube root of 200. And this is in centimeters. Now again, how would you check that this is actually a minimum? You could go to the second derivative test, and you could check what the second derivative is, and plug in this x value and see. But this right here will be an absolute minimum. OK, let's move on to this example right here. So we're going to find the point on the line 6x plus y equals 9 that is closest to negative 3, 1. OK, so what I'm going to do first is I'm going to go ahead and I'm going to draw a picture. So this is a picture that you'd see in algebra. I'm going to draw the equation of the line. So what I'll do is I'll start with my picture. I'll give myself some markings like this. maybe some like here and here. I'm going to rearrange this into slope-intercept form. So this is the same as y equals negative 6x plus 9. So that's the exact same thing. So I'll go ahead and draw that. The y-intercept is 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. The slope is negative 6. So I'll go down 6, 1, 2, 4, 5, 6, and over 1. And this gives me an estimate for what my line looks like. Now, there's this line, but there's also this point that they're indicating. So negative 3, 1 is the point over here. So this is negative 3, 1. And what we want to do is we want to be closest to that point. We want to be somewhere on this line, but closest to that point. The way you're going to be closest is if you have a straight line path to here. So somewhere right here. This is the point I'm looking for. It's on the line, and it's the shortest distance. You wouldn't pick something over here, because that's very far away. You'd pick something as close as you can get and still be on the line. So when it says closest to, we're minimizing something. And we're going to minimize the distance. So in disguise, that's what this means. So if you let D represent how far this is, wherever you are on this line, we're trying to minimize what the distance is. So for my labeling, I'm just going to say D is the distance, and then XY is a point on the line y equals negative 6x plus 9. So that's my labeling. Those are my variables. Let's take a look at the equation now. So the distance has its own formula. So distance is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. So it's the distance between some point xy and negative 3, 1. We can call this one x1, y1 if we want. And you could say that this one maybe is x2, y2 right here. So let's plug this in. So we're going to get x minus, and then x1 is negative 3, so this is plus 3 squared, plus y2 is y, minus 1 is my x1. And this is the equation. I'd like to minimize this. However, there's more than one variable. So for we have to eliminate the variables. So how do we do it? Well, this y right here, we know an equation for it in terms of x. Y is equal to this right here. It's the line. So instead of y, I'm going to plug this in. So d is equal to the square root of x plus 3 squared plus, and instead of y, we'll replace it with what we know y is. This is going to be negative 6x. If I plug in plus 9 minus 1, I get plus 8 squared. So that's where we are so far. Now what I'm going to do is, instead of taking a derivative of this, I'm going to think for a moment. So distance is always at least 0. So if I were to square the distance, square some kind of positive number, then whatever x will minimize this expression is also going to minimize this number squared as well. And I'm making that insight because it's much easier to take the derivative of this expression squared than it is to do the original. So because this is a positive number, the same x that minimizes this is going to minimize the next equation I'm going to write. So we're going to minimize d squared instead. And I'm just going to call this, we're going to say that capital D is going to be the distance formula squared. So capital D is equal to, we'll square this, and what that does is it just gets rid of the radical for us. It just makes taking the derivative much, much easier. That's all we've done. OK? I'm going to go ahead and use the chain rule now to take the derivative. So this is step 5. We're taking the derivative. We're going to find that critical point. which minimizes this situation. So chain rule says it's 2x plus 3, no derivative for the inside, plus, bring this 2 down, 2, rewrite the inside. Derivative of the inside is negative 6. And to find the max and mins, what you do is you set the derivative equal to 0. So we're going to solve for that x value that does that. Continuing here, this tells us 2x plus 6 minus 12x plus 16. So this is, minus, this is all times negative 6. I did that in a funny order. Let me go back here and just do that one more time. I don't like the order I did that in. So this tells me that I have 2x plus 6. Negative 6 times 2 is negative 12. And then negative 12 times this number right here is positive 72x. And then negative 12 times positive 8 is minus 96 equals 0. I'm going to combine these. I get 74x minus 90 equals 0. So x should be 90 over 74. If I divide by 2, that's going to be 45 over 37. So the x-coordinate that minimizes the distance is at 45, 37. So what I just found is right over here. So if I go to my picture, this is why having a picture is good. This point right here, the one that's on the line and closest to this, the x-coordinate right here, we just figured out that this is 45 over 37. So it's actually a little more than 1. So my picture is kind of off. But this is the x-coordinate where we're going to minimize the distance. To find the y-coordinate, all you do is you would plug the x-coordinate into the original. So that would be negative 6 times 45 over 37 plus 9. So this is the point that's on that line. That's this straight distance to negative 3 over 1. All right, so I hope that was clear. Remember that when you do find these critical numbers, you can always go back to the second derivative and double check that it is indeed a max or a min. So that would be a good exercise to do for these two, just like I did in the very first example. OK, I think that wraps it up for this lecture. Try out your quiz and send me questions if you have any. I'll see you next time.